So the last thing we talked about last time was the notion of a set of connecatives, a set of truth functions is adequate if compositions of those functions can express every truth function. So that was the main definition. And just to recall, a truth function is a function f that goes from tf to the power n to tf for some n, and can be thought of, can be expressed by a truth table. So we can think of them as truth tables. A truth function is a truth table over n variables. So you have P1 up to Pn. And here you have f of P1 up to Pn. And they can take all possible Tf vectors. So such a table has 2 to the n many rows. So that's a truth function. And what we showed is that we have shown that the set consisting of those 4 functions with their truth tables is adequate. Right? And to just give you again a sense of the proof, because it was just the end of the class, and demonstration here is just as good as a full proof. The idea was that assume that I have such a truth function. So let us look at an example, which I think examples here is just as contains all the information that we need about the proof. So assume that we get some truth function, say, to make it concrete, have here 3, n equals 3. So I have P1, P2, and P3. And here I have some function, a concrete function. So I start with TTT, then TTF, then TFT, TFF. And now I repeat all this with the first letter being F. So I have FTT, FTF, FFT, and FFF. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's what we expected, to have 8 lines. And assume that I take some arbitrary function. So I have no particular meaning to this function. So we just pick randomly, right? So let's do it randomly. So every head will be, so you draw it, tell me when it's head or tail. Tail will be 2, a T, so? Tails. Okay. That's okay. What? Heads.
Heads. Tails. Tails.
We have a biased coin.
Heads.
Okay. Okay, so now, no. Sorry, not heads, but F. Okay. So now I want to express this function. I want to express this function with the connectives that I have there. So what am I going to do? I'm giving them names for each line. So this is alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, alpha 8. So each row gets a name. And for each row, I get a formula that exactly describes the situation of this row. So alpha 1, sorry. Alpha 1 is going to be the formula P1 and P2 and P3. And alpha 2 is going to be similarly, right? The formula P1 and not P and P2 and not P3. And so on. But I don't have to write all of them. So for every row, I pick a formula that describes exactly the assignment of this row. So the special thing about the alpha I is that the only assignment that satisfies alpha I is the assignment that I see here. That's the only assignment that satisfies alpha I. And now I'm only looking at those that end up with T. And I'm saying my formula alpha of f that will describe the function f is going to be just the O of all the descriptors of T's. So it will be either P1 and P2 and P3. Or next time I get a T is here. P1 and not P2 and not P3. Or next time I get a T is here. So it's not P1 and P2 and P3. Oh, so we took care of this guy. You gave me too many T's. Oh, not P1 and P2 and not P3. So we took care of this one, and now this is the last one, which is O, not P1 and not P2 and P3. So that's my formula. And why is this formula equivalent? What I'm claiming is that the truth table of alpha f is clearly a formula that is written only with our connectives. In fact, it only uses 3 of the 4 connectives. And why is it equivalent to f? Because if I'll try to ask which truth assignments satisfy alpha f. So in order to satisfy alpha f, I need to satisfy one of those components. So in order to satisfy alpha f is, in fact, alpha f is alpha 1, or alpha 4, or alpha 5, or alpha 6, or alpha 7, right? It is just the O of the descriptors of the lines in which I got to. So if I want to say, I ask, when will this formula get T? It will get T either if I satisfy this one, or satisfy this one, or satisfy this one. But to satisfy alpha 1, I have to be in the first row. To satisfy alpha 4, I have to be in the fourth row. So this formula will get T exactly in the same rows that f gets T. And therefore, they have the same truth table. Does it make sense? So that's actually our proof. We describe each row in which we have t by a formula that is satisfied only by this assignment. And now we say, I'll get t if and only if I am in one of those assignments. So the truth table of alpha f is going to be the same as the truth table of f. And of course, we can do it for any function, regardless of how many variables there are. In this case, we had 5 rows with a t and only 3 with an f. So can anybody think of a shorter way of describing this? Yeah.
If we take the 3 rows with f and combine them in the same way, but just not it, it should be equivalent, right?
Right. So just be a little bit careful. I want to say that I'm going to fail here, or fail here, and fail here. So what am I going to say? I'm going to so if I take what I can, another way of describing the same, another formula that will describe the same f is going to say I will take alpha 2, which is an f, and I will take alpha 3, which is an f, and I'll take alpha 8, which is an f, and I want to say I will be true if I'm not in any of those. Right? So I can say I'll get true if this one fails. I'll get f if one of those holds. So what happens if, I think, can we just take the negation of the whole thing? Let's see. Is this a good solution? Take the negation of all of those things, which means I will succeed if I'm not in one of those rows. Right. I'll get a true if I'm not in one. Because if one of them gets true, which I'm either in row 1 or row 3 or row 8. In those cases, I want to get f. If none of them gets true, I'm in the other rows, and then this will be false, and that will be true. So this is another, call it alpha prime of f. It's a different formula that also expresses the same truth functional. But in any case, we see that all we need is the and ors and the not. So the conclusion from this discussion is that so the conclusion is that the set that contains just these 3 is adequate. And furthermore, note that if a set S of functions is adequate and S prime is a superset of S, then S prime is also adequate. Right? Because if I can express everything just using S, I have more functions in my set. I am not forced to use them. I can still express everything and just use S. So the corollary from this, is that the system that we used is adequate. Because it's a superset of an adequate system. And it is a phenomenon that you have seen. I mean, this is something very similar to programming languages. You know that any single programming language that you come across is rich enough to express any program. You can write any program in C. You can write any program in C++. You can write any program in Python. You can write any program in assembly. All of them, each of them can express every program. It's just a matter of convenience. Which one do we choose for a specific type of programs? Right? So we could just similarly talk about the adequacy of a programming language. Each kind of a language that allows me to express certain things. I want to be able that I can express everything in this domain. Here, to express everything means to be able to express every truth functional, because propositional calculus cannot do anything beyond truth functionals. It only computes the outcome of a proposition based on the true-false values of the components. Any questions? Someone looks troubled. So let us check a little bit, play with this a little bit. Two things we want to show. I want to show you that there are systems which are even smaller systems which are still adequate. And I want to show you that some systems are not adequate. So we want to have tools to be able to distinguish, to check whether a given system is adequate or not. So let's now, after we saw a positive result, let's see a negative result. So I have here a claim that the system, or the set of connectives that contains and or an error is not adequate. So I claim that if we delete the negation, it is not going to be adequate. Now, how can we prove it? So what is the idea of proving such a claim? So to show it's not adequate, I have to show you that there is some function that you cannot express. So I can either show it for a specific function, or going again to the IAP and the generalized induction, what we want to show is that we wish to show that there exists a truth function f such that f is not a member of I, and here I have propositional variables. And here I have my operations, but only these three operations. Only these three operations. So I write all formulas. I start with the propositional variables as usual. But when I do my closure to generate new formulas, I'm only using those three operations. And I want to show that there is a function that is not there. There's a truth table that I cannot express with those. Yes?
Let's say you were giving a specific example for this proof, and then how do you prove that this is either cannot be expressed by the given IAP, but rather is that you cannot find a way to express it?
Right. I want to show that you cannot find a way to express it, these formulas, right?
I mean, maybe it's not not exhaustive, so that even you can't find, maybe someone else could.
Yeah, I'm not talking about my ability to find. What I mean by this is the set of all functions that you can get by starting. The propositional variables, you can look at them as the identity function.
Yeah.
The propositional variables, you can look at them as a function. So the propositional variables, you can look at the function f of p, that given true, f of p has only one variable p, and it's the identity. So f of p of a variable p, or a variable q, whatever, I don't know. OK. Of any variable is just the identity. So fp of t is t, and fp of false is false. And now each of those, each is just a function, a truth table. Yes?
And all I mean is, like, IAP, in this case, is an infinite set.
Right.
So you cannot taking every specific combinations of it to prove that f is not equal to them by you.
Yeah, but that's our usual problem of showing that something is not in IAP. Usually IAP is going to be an infinite set. So how do we show that something is not an IAP? I find a property. So here I have my A, and here I have my IAP. And how do I show that something is not in IAP? I want to find some property that I will be able to show by induction that everything that I generate satisfies this property. So I want to find some property that I will be able to show by induction that each of them satisfies it. And then I'll find some f that doesn't satisfy the property. OK? So I want to take some property and prove that anything I can generate like this has this property. Any function that I can generate like this has this property. OK? So now let us prove. Pick the property that f of t equals t. So the property is our function vt of our function is true, where vt is the all t assignment. So I want to show that everything that I can generate from this connective has the property that when I substitute the all true assignment, the output will be true. And then which f should I pick here to show that I wasn't able to generate all f's? For example, negation. So here we can just put the negation function. So I will not be able to express negation because negation does not have this property. So now we reduce the problem to a problem that we can address by generalized induction. So let us show that this applies to every pf in I, A, this P by generalized induction. So what is the base case? The base case of the induction? I have to treat the propositional variables. But the propositional variables are the identity functions. If I take a propositional variable and substitute t, what I get out is t. So this trivially holds for alpha equals p, for any p. And now the induction step. So we are given, assume alpha 1, alpha 1, alpha 2 satisfy the claim, and show that so do. And now we have to show that for alpha 1 and alpha 2, alpha 1 or alpha 2, and alpha 1 arrow alpha 2. So for each of those, I have to check what will be the output if I substitute the all t assignment, truth assignment, right? So what will be, for example, Vt of alpha 1 and alpha 2? So to do this, I'm looking at the truth table of end, and I'll have here alpha 1, and I'll have here alpha 2, and here I'll have alpha 1 and alpha 2. And now I just look at the assignment which is all t. And I want to see what will happen here. So what will happen here? What will be the truth value of alpha 1 under the all true assignment? How do I know it? Not the base case, the hypothesis, the induction hypothesis. So this is exactly the induction hypothesis. And this is also the induction hypothesis. So I'm using the induction hypothesis. The induction hypothesis was that for alpha 1 and alpha 2, under the all t truth assignment, I got t. And now, how will I get t here? What will I use now? Truth table of end. This is by the truth table of end. If I already know that this is t and this is t, I can use the truth table to conclude that alpha 1 and alpha 2 will also get t. And we just have to repeat it for each of those three connectives. And we know that for each of those three connectives, the first line, the line that corresponds to the all t truth assignments, calculates to true. OK? So all we do now is just repeat it for this guy and repeat it for this guy. So we got a proof that if we delete the negation, it will not be an adequate set of connectives. Does it, are there any questions? So if you want to show that a certain set is not adequate, we work by generalized induction. We have to find a property that is common. We'll prove by induction that this property is common to everything you can generate, and then find a function that fails that property. This one was very easy, of course. Sometimes it takes more thinking to find out such a property. So this will be the content of your next part of the content of your next assignment. I want to also show you a positive result. So now let's see a positive result. Here is another claim. And I claim that the set that contains only negation and O is adequate. So now the proof is even simpler. Yes?
Technically, if we show that we can implement and.
Exactly. If we can implement and using those guys, we know that once we have at our disposal not and or and and, then we can have everything. So it suffices to show proof. It suffices to show that this system can express every connective in some known to be adequate set S. So in particular, right, because if I can express every component of an adequate system, now I have some function. I will first express it by the adequate system, and then I replace all the components by something expressible by these guys. So in particular, it suffices to show that we can express the truth table of the missing guy and by negation and O. Because then we'll have all the components of an adequate system, and we can then use them to express every function. Okay, so how are we going to do it? The claim is we're just coming up with, we just know it. What is the, how do I express and? Yes?
De Morgan's law.
By De Morgan's law, right. So if I have here a P1, P2, and I want to express the end, let me just write it. Okay, I'll write it directly. So it just, the end is just not P1 or not P2. So we can just check the table and see that what we get is exactly the same table as the table for end. Because if both of them are true, then this is false, and this is false, and this is false, so this is true. Sorry. Okay, false, false, all of the two falses, I get a false, negation, I get a true. If I take TF, I have here false, true, so this is true, so the negation is F. Same thing here. The negation will be F. What happens if I take FF? So this becomes true, this becomes true, the OR of the two is true, I negate it, I get an F. And what I see here is exactly the table for end. So we found a way to express end. So this is an adequate system because we just brute force came up with a formula with a way to express end. Yes?
I know in an assignment we wouldn't get one this easy, but will we have to show the table, or can we just say by De Morgan's law we know that this is equal?
Yeah, I mean,
I know that on an assignment it would be a bit harder, so maybe it should be like a little more.
no, it's okay to say it as long as it's true. I mean, it just, I advise you to check well. Yeah, if you say it, and it's true, then I trust you that you can check a truth table.
I'm not sure you want to make that statement, because then you could answer all assignment proof questions by saying it is true.
No, I'm just talking about, yeah, it's a good comment just to clarify myself. What I mean is whenever you claim that a certain formula computes to a certain truth value, you can just claim it. Okay? It's just about computing truth values, not about anything smarter than that. And we will get back to, I think, maybe the lecture next week or the lecture after that, we'll get back to this issue. Because, you see, now we don't talk about proving in our system. In our system, we're just talking about semantics. A proof is something in the syntax. And when we start talking about proofs in the syntax, we'll exactly want to ask ourselves, what do we require from a proof system? Why can't just claim this is true because I said so? Why is it not a proof? I mean, it's a proof if I say so, not if you. OK, so we will get back. It's a serious question. In your case, you can allow yourself to make such statements about the truth values of a specific formula, and I'll trust you. Oh, I'll check it. OK, so we have a way of showing that the system is adequate. We have a way of showing the system is inadequate. I have a few tools with which I can play some tricks and questions, and you will see it in the next assignment. That's all I wanted to say about it so far. And the conclusion also is that the reason why I chose those 4 connectives was just for convenience. It's easier to express natural things with those 4 connectives. I could have just done everything with just 2 of them. And in fact, there is even a system with only 1 connective that is adequate. And that's the system that with the NAND. So we can have only 1 connective, which is either NAND or no. So if I have here P1, P2, and here I have the NAND of P1, P2, and it's just the truth table of the negation of AND. So TTF, and everything else is T. And it turns out that this single connective is adequate. But you need to do more calculations to show it, to express any. All you need is to express. I mean, it's also easy to see that this is adequate, and negation and AND is adequate. So to show that this guy is adequate, it suffices to show that you can express these 2 with it. Anyway, so this is as far as I want to talk about adequacy, and we move on. OK, so then I want to talk more. So we are still in the semantics, and I want to talk a little bit more about sets of propositions. So what do we know so far about semantic notions for sets of propositions? So what we saw so far is 2 terms. One of them was we saw 2 notions. One was that sigma is satisfiable, and that meant that we had a truth assignment that satisfies every formula in sigma. And the other one was that sigma logically implies some alpha. that every truth assignment that satisfies every member of sigma also satisfies alpha. And now I want to introduce two more notions. So here is a new one. We will say that, so a new notion. We will say that sigma is complete if for every propositional formula alpha, either sigma logically implies alpha, or sigma logically implies the negation of alpha. So it's a kind of a set of assumptions that is very opinionated. For every statement that you bring up, it has a strong opinion. It says either it must be true or it must be false, no matter what question you ask. So that's a strongly opinionated sigma. So can you give me a trivial example of a complete sigma? Yes?
Just false?
What do you mean just false? Sigma should be a set of formulas. So I want a set of propositional formulas.
The set containing like every variable going to not that variable? Like it has to always return false.
I'm talking about a set of formulas. So you just give me the propositions. So suggestion one, if I get you correctly, what you mean is not P1, not P2, not Pn for every n.
No,
No.
because sometimes that, he means a set of entirely contradictions.
Yes.
Because
So-
then it'll imply everything vaguely.
Let's look at sigma 2, which is just much more simple. Just have P1 and not P1.
Yeah.
Yeah.
OK. So sigma 2 is a good example because remember by the Russell story and the Pope, we know that if we start from a contradiction, everything is logically implied. So for every propositional formula alpha, either it will prove alpha, or it will prove not alpha. Actually, it will do both. Right? So the interesting, it's kind of redundant. You say, I mean, there is this guy that is very opinionated. He has a strong opinion on everything. So you ask him, should I go out tonight? He tells you no. And you ask him, should I not go out tonight? He says no. Anything you ask, he just tells you no. OK, he's very opinionated, but it's not consistent. So let us improve it a little bit. So let's say that sigma is a complete and satisfiable. It's not a very, it's the obvious thing, right? If it is both, if it is both complete and satisfiable. A very kind of, if you never studied this for the exam and you get this question in the exam, what is sigma being complete and satisfiable, you have an easy answer, right? Now, the not so easy is, can you give me an example of a system which is both complete and satisfiable? And note that completely satisfiable is the same thing as saying that instead of having or here, I will add but not both. If I add, so such sigma has for every alpha, sigma logically implies alpha, or sigma logically implies not alpha, but never both. And this is an exercise for you. Prove it. So can you show me such a system that it's complete, but yes?
If the sigma contains alpha, then the system would always be
Who is alpha?
the formula.
Well, yeah, but you want to show that for every formula. It's complete if the main point here, this should happen for every alpha. If I put all the alphas into sigma, what will happen? What?
Sigma will be a contradiction.
Right, it will not be satisfiable. If I put all the alphas into sigma, it will not be satisfiable because there will be p and not p. So I want to make it satisfiable without making it, I want to make it complete without violating satisfiability. So it's not very difficult to find an example. I'll tell you why it's not very difficult. Because the example is on the board. Like, look at this guy. Why? Yeah, it's my interpretation of what you were saying.
Your
Right.
incorrect interpretation. I'm going to claim that was mine. You corrected it. You misrepresented. Yeah, that was definitely what I was going for.
Right. Okay. So first of all, why is it satisfiable? Do you have a truth assignment that will satisfy it? All false. If every variable is false, then each of those formulas will be true. Now, why for every alpha it either implies alpha or implies not alpha? Because there is only one assignment that satisfies it, the all false assignment. So if alpha under the all false assignment is true, then this y implies alpha. So what I'm saying is that sigma 1, this guy, sigma 1 logically implies alpha if and only if VF of alpha is true, where VF is the all F assignment. Because if sigma 1 logically implies alpha, it means every assignment that satisfies sigma 1 must satisfy alpha. But there's only one guy that satisfies sigma 1. It's the all false. And therefore, it means that if sigma 1 implies alpha, the all false assignment should give alpha the value true. What about the other direction? Assume that the all false assignment gives alpha true. If the all false assignment gives alpha true, then every assignment that satisfies sigma 1 will give alpha true, because every assignment that satisfies sigma 1 is the all false assignment. Right? So sigma 1 implies, logically implies alpha, if and only if alpha is true. But now you can see that for every formula, either under VF alpha is true, or if alpha is not true over VF, not alpha will be true. So therefore, for every alpha, either sigma 1 logically implies alpha, either VF gives it true, otherwise VF gives it false. So or sigma 1 logically implies the negation of alpha. Because if VF gives it false, VF gives this guy true. And we said that if VF gives one true, it is logically implied. So can you give me now another example of a satisfiable and complete set of formulas? Yes?
The set of all propositional variables.
Right. Why take negations there? Why be negative? So let sigma 2 be just the set of all propositional variables.
Why overcomplicate things? Why not one propositional variable?
Because then, if I take only one, if I take sigma 3 to be just P1, then the problem is that sigma 3 does not logically imply P2, and sigma 3 does not logically imply not P2. It says nothing about P2. But we want a system that will say something about every formula. So I need to take all the propositional variables.
Wait, can you explain why sigma 3 does not imply P2?
Very good. Why is not imply P2? Because I can find a truth assignment that will satisfy everybody in sigma 3, but will not satisfy P2. Take the truth assignment V of P equals false if P is P1 and true if P is P2. This is an assignment, right? It gives what? The other way. Right. False, so true for P1 and false for P2. So this assignment satisfies every formula in sigma 3. In sigma 3, there's only one formula. It's P1. This V will satisfy it. But it does not satisfy P2. Because for P2, it will give me F. So I showed that there exists an assignment that satisfies sigma 3 and doesn't satisfy sigma 2. And doesn't satisfy P2. But it was a very good question. To show that sigma does not. So it's a very good question. How do I show that sigma does not logically imply a formula? I just show you an assignment that satisfies sigma and not the formula. So here is another example. So I claim that if my sigma is, say my sigma is P1 and P1 or P2, right? It does not logically imply P1 and P2. So how do I know that this sigma does not imply this alpha? I have to find a truth assignment that will satisfy every guy here, but will falsify this guy. And my truth assignment will be give this guy true and give P2 false. So both of them will be satisfied here, and this will not be satisfied. So the truth assignment, the assignment V of P1 equals true, V of P2 equals false, demonstrates this no logical implication. Right? So to show that I have a failure of logical implication, I just come up with an example. Okay, so far we have two examples of complete systems, or three examples of complete system, but one of them is not satisfiable. We have two examples of complete and satisfiable systems. Can you give me another example of complete and satisfiable system? Yeah.
Not P1 and then every other propositional variable.
Right. Whenever I set all the variables to a specific value, then it's going to be complete and satisfiable. So I can do not P1, not P2, not P3, and everything else, P4, P5, P6. I'll include everybody either with as a propositional variable or with negation. If I dictate the truth assignment, then it's satisfiable and complete. So let us try to make this more formal. So these were just examples. This was a definition. So I'll continue from here, because from here it was just examples. So let us look at another property of such a sigma. Maybe just before that, for those of you who studied linear algebra, what does this remind you? Being satisfiable and complete, it is very similar to having a basis for a vector space. So what is a basis for a vector space? It is a set of vectors which are linearly independent. Linearly independent, you can think of it, they are not contradicting each other here. And they span the whole vector space. They span the whole vector space. Here it means for every alpha, they either prove alpha or not alpha. So it's kind of, you have a notion of satisfiable and maximal satisfiable is what we care about. And it's the same as, I mean, it's very similar to a vector space, to a notion of a basis. It is independent and it spans everything. So now we want to show that those two things, okay, so now I'm being carried away with the analogy. Which of you have seen this theorem that knows what the basis for a vector space is, and saw the theorem that a set of vectors is a basis if and only if it is maximally independent?
What do you mean maximally independent?
Okay, so you haven't seen it. That if you try to add any other vector, it will become dependent.
Oh, yeah, we have seen that.
Yeah, linearly independent.
What do you call it?
It's like, it's basis if it's linearly independent and spanning, and it spans the whole vector space.
Okay, so just for those who remember the algebra. In algebra, we had the following theorem from algebra that says that a set of vectors A in some vector space V is a what? Is a basis, right? But if, the following is if and only if it is a linearly independent set and it spans V, and this is if and only if it is a maximal independent set. Maximal independent set means that every other vector that you will try to add to it will make it dependent.
I think we just used the definition of the basis is the smallest set that is linearly independent spans, which ends up doing the same thing.
Okay. But anyway, this is a result in algebra, and now we're going to do a very similar result here. It has a very similar structure. So what do I mean here by being maximally independent? So let us say that sigma is maximally satisfiable if sigma is satisfiable and for every alpha if sigma does not logically imply alpha, then sigma union alpha is not satisfiable. So if I want to add something to it, I will get inconsistency. So in what sense, in the same, if sigma is my set of opinions, so being maximally satisfiable means that my set of opinions does not contain a contradiction. But if you try to tell me some new fact, either I know it already, it is already implied by what I know, or otherwise it will contradict one of the things that I already have. So I'm not open to learning new things. Anything you try to teach me, I'm telling you, either I already know it, or I don't believe it. That's this maximally consistent, maximally satisfiable set, right? And now, exactly like this theorem in linear algebra, we have a theorem that says that two notions are the same here as well. So it's very similar to the situation in linear algebra. So for those who care about, who know about this linear algebra, there's some kind of common themes that go through many areas, through many branches in mathematics. And this is one of them. And we have here a theorem, which is not very difficult to prove. So we have here a theorem that says for every set of propositional formulas sigma, the following are equivalent. And one is sigma is complete and satisfiable, and two, sigma is maximally satisfiable. So you see that these are two different notions. One of them says complete, both of them say satisfiable. So in that respect, they're not different. In what sense are they different? This guy is saying for every alpha, either I logically imply alpha or I logically imply not alpha. And this one saying for every alpha, if I don't logically imply it, you cannot add it without hurting, blowing up the satisfiability. Okay? So let us show that 1 implies 2. So proof. So I have this direction from 1 to 2. Oh, wait, let me write it like this. 1 implies 2. So let sigma be complete and satisfiable. Now, given alpha, if sigma does not logically imply alpha, then what will I get? Then, by completeness, I get that sigma implies the negation of alpha. Therefore, sigma union alpha is not satisfiable. I cannot satisfy all the formulas of sigma and alpha, because if I satisfy all the formulas in sigma, I must satisfy not alpha. If I satisfy not alpha, I cannot satisfy alpha. Right? This says whenever you satisfy everybody in sigma, you satisfy not alpha. This one says, find me someone that satisfies all of sigma and satisfy alpha. I can't find it. So it's not satisfiable. So we showed that 1 implies 2. Any questions here? So what about 2 implies 1? So we assume it's maximally satisfiable. And I want to show that it is satisfiable and complete. So the satisfiability I get for free. Why is it complete? Right? So assume let sigma be max satisfiable. Need to show it is complete. So we pick any alpha. Pick any alpha. I need to show that if it doesn't imply alpha, it implies the negation of alpha for completeness. So either sigma logically implies alpha, or if sigma does not logically imply alpha, then what do I know by maximality?
The union is not satisfiable.
The sigma union alpha is not satisfiable. What does it mean? Namely, any assignment V that satisfies sigma fails to satisfy alpha. I cannot find someone that is satisfy all of them. So whenever I succeeded on this side, I'm failing on this side. But if this assignment doesn't satisfy alpha, therefore, such assignment satisfies, it fails to satisfy alpha. So it satisfies not alpha. So sigma logically implies not alpha. So this is kind of a confusing game because we are all the time kind of just juggling around with the definitions. But it should not be very difficult once you get used to the definitions. And I'll finish this lecture with one more property, a third equivalent property that I will leave it to you. I really think that those kind of part of this is much more useful to try to do it on your own than to follow me doing it. So I'll give you another property and try to show that it is equivalent to these two. So here is a thinking exercise. Prove that any sigma is maximally satisfiable or satisfiable and complete if and only if there is exactly one single V that satisfies all formulas in sigma. So we found a third equivalent property, which is it dictates a unique satisfying assignment. It is satisfiable, there is a satisfying assignment, but only one. Okay? So that'll be all for today. On Tuesday, Aaron will replace me, and there's no office hour next Wednesday. There will be on Friday.